Today's pretty exciting because we're going to start learning about the C programming language. I'm also calling this lecture Computers in the Universe because hopefully through the lecture you'll come to see that while we're going to focus on one particular programming language, it's going to point to things that are much deeper and much more important about the structure of problems and the structure of the universe. And you might be thinking, you know, I learned Python, I didn't learn anything about black holes, what's going on here? But as we go through the lecture, you'll start to see elements of the deep links between mathematics and computer science and physics. So why are we learning a different language in the first place? We already know Python. Why are we bothering? Python gives you a particular way of thinking. The way that one programs in certain types of languages is different from others, not just in the words you use, but in the cognitive processes that you undergo in order to formulate your problems. Was that a question? No. Okay. There are a bunch of different paradigms that into which we divide different programming languages to ease categorization, and so you know which of the different ways of thinking might apply to a given language. One distinction is compiled versus interpreted. And this might not look very different on the slide, and that's because at a fundamental level, there is always a translation process happening inside your computer. For a compiled language, the translation process is you write your program in text, and then it gets converted to instructions that look like the ones over there. They get passed through to the circuitry, and then the circuitry performs the computations and hopefully sends something back to the screen. An interpreted language is actually the same. The only difference being, after you've written the text, you feed that text into another program that's constantly running, and as it goes along, it's generating new machine instructions as you need them, rather than all of them ahead of time. This comes with some extra flexibility and some extra power, but also a lot of extra costs. C is a compiled programming language. This means that unlike Python, where you run the Python command to execute your program, in C you're going to run a compiler that translates the program and generates this set of instructions, and then you'll be able to run the program itself. You'll be able to run the program itself because you don't need the Python program that is constantly running to translate the Python instructions. You're going to have already converted it directly into something that the machine understands. This is one categorization, but there's also another. There is a division between different types of programming languages based on the form in which you represent your instructions. And what do I mean by that? Well, Python is primarily an imperative language. What this means is that you give the computer an ordered flow of instructions, and one by one, it performs those instructions, and altogether, if you follow the sequence, you'll get a result that you inserted into your code. But that's not the only way that one could imagine a programming language working. What about if we just told the computer what kind of problem we wanted to solve, and then the computer just went ahead and did it? This might sound a little far-fetched, but if you're willing to formulate your problem in such a way that there's a companion program that goes along with it and understands the type of problem you're trying to solve, maybe you can just go ahead and declare what you want the computer to do, and this helper program will be able to translate your wishes into the goal. So that's a different form of programming. Yes, it's not as close to the metal, you're not writing machine instructions, but it's still a legitimate way of approaching programming. And functional programming language, which hopefully you'll cover a little later in your degree, is another one of these paradigms that aims to match a closer analog to mathematical thinking. So why learn C specifically? So I've given you all this tosh about different programming languages and how there are all these varieties. Why C in particular? C is interesting in that it allows you to make a lot of mistakes, but in a positive way. It's very closely tied to the design of the underlying computer. So if the computer thinks about memory in a certain way, C is probably going to think about memory in a very similar way. It's also one of the most broadly used and best known languages of all time out there. And despite its longevity, it's survived a very long time and is still in place in modern systems today, like your operating systems, which are probably written in a mix of C and perhaps some other C variants or languages that were later derived from C. C is also small, it's fast, The programs are run almost universally. There's a C compiler, this translating program, available for pretty much every architecture out there, which makes it very easy to get a C program in one place, compiling in another place. And on top of all of that, there's also a lot of history of teaching undergraduate C, and you are all soon going to be part of this very long-standing tradition. But can it teach us deep truths about the universe? I don't know. And this is going to be a slide that many of you, I'm sure, will come back to me with questions later in semester. Why should we not learn C? It turns out there are actually a whole lot of good reasons. It is very easy to make mistakes in C. In Python, you do maths, and the maths works. If you multiply something by 10 and divide it by 10, you'll get your original answer back. In C, the computer doesn't always do this. And one of the components of the first few weeks of the course is learning all these quirks of the C programming language and the different ways to screw things up. This is also why we really, really encourage you to spend a lot of time on Grok and doing the exercises, because things aren't always intuitive, and until you make the mistake, you might not remember it. C is also not type safe. What this means is this is another protection that modern programming languages have to prevent you from making mistakes. C removes that. It gives you the complete power to control the computer and the complete power to control the computer wrong. C also has old-fashioned tooling and a whole lot of like, what were they thinking issues, like that division by 10 issue, which kind of is very unintuitive and leads you to question why the language was designed that way. If you spend a lot of time with it, it turns out there are generally good answers to a lot of these questions, but it will make your lives a little frustrating over the next semester and also give you a sense of accomplishment once you're actually past it. So C was first envisioned in 1969 primarily by Dennis Ritchie over there, but Brian Kernighan, and they were both employees at Bell Labs, and Brian Kernighan collaborated with Dennis Ritchie to write the first textbook on the language, which is still a hallmark of the C language, and it's called, in fact, the C programming language, or K&R for short, for Kernighan and Ritchie. And this was a pretty impressive development over prior languages because it achieved a very sophisticated balance between expressiveness, the ease with which you were able to tell the computer what you wanted to do, but also power. It was very, very powerful, even in contrast to some other languages that had been around at the time, which were very expressive, but not very powerful. So it was easy to tell the computer what you wanted to do, but you couldn't do very many things. Not sure. Liam, did you select sound on this?
I didn't. I forgot, sorry.
Oh well. Anyway, this is a video of, you can go ahead and do that now. This is a video of Bell Labs. It's the facility where the transistor was born and where many of the modern precepts of programming and computer science were born too.
That's the way it's been at Holmdel, then and now. For more than 50 years, Holmdel has been the setting for new developments, discoveries, and applications of technology and telecommunications. Since 1962, this work has been done in this immense, dynamic building.
Bell Labs was the source of many important modern inventions and was actually one of the few private institutes to achieve a Nobel Prize. It was an outshoot of the US telecom monopoly's hold on the market, which left them with a lot of finances able to invest in fairly blue sky research projects. So as we go along and use all these tools to not only program, but to assist our programming and to navigate the operating system, we'll actually encounter a lot of different tools and artifacts from Bell Labs. In fact, many of my instructors were originally employees at Bell Labs before moving to academia when Bell Labs ultimately shuttered. As I said, C was the fairly early language, and it inspired many subsequent languages. So another answer to why are we learning C, which, oh, sorry, this was the slide that shows the development of different operating systems. So up at the top there is Unix, which was the operating system that was developed at Bell Labs along with the C programming language, and that was written in C. And then if you trace it along, you can start to get many of our modern operating systems, down to this one over here that you'll remember, Mac OS. So Mac OS is ultimately a product of Bell Labs, and as is Linux, which is over here. Windows actually came through a different development cycle that wasn't part of Bell Labs, But still, Windows did use many of the same programming tools and language design artifacts that did come from this place. And so it's worth knowing about it because it will be a feature probably in many of and this is a very similar slide, but showing the development of programming languages. And if I can find C on this giant thing, it's over there in the box. So C developed from B. To answer the question, yes, there was a B. I'm not sure if there was an A, though. But if we look along here, we can find all the modern programming languages that you've probably heard of. So like C++ over there. There we have Python, and then Python 1.5. Hopefully all of you were learning Python 3 in your prior course. And over here we have Java. So one of the answers to why C is because all of these other modern programming languages, there's JavaScript over there, all branched out using various different elements of the C programming language that inspired them. So you can see Java here as a mix between Simula and C. A little bit of Simula, a little bit of C, a little bit of some other things. And so this is another answer to why we're bothering to learn this, is because the same ideas that are part of C are part of many, many modern operating systems. And it is not moving forward on the slide. Oh, there were animations. OK. So it's finally time for us to write our very first C program. And if I could Alt-Tab, that would be helpful.
I don't know why the Alt-Tab's not working.
We'll still screen share the other screen? Yeah. There we go. OK. So we're ready to write our first program. And a C program, at the end of the day, is just some words on a page. There's a standard, there's a set of agreed things that programmers have gotten together and said, this will be the C programming language when you write words like this, but ultimately, it is just words. We need the compiler in order to convert those words into a running program. So let's open up a new file and call that helloworld.c. It's going to give me some warnings about ways that I haven't set up the program quite as it would like, and I can't actually see those warnings. OK, we're just going to create a new window. So the nano command is a different text editor to the one I was just using. I'll have to look into that later. And we're going to create a file called helloworld.c, which I guess I already wrote. We'll create a file called helloworld2.c so we can do it from scratch. The first thing we're going to do is add a little magic, and we'll explain what this magic is a little later. But it seems if we treat this at face value, it seems like we're adding something into our program from somewhere else, including something. And this something is called stdio.h, standard input and output. OK. Some more mystery. And finally, we get to the actual command. And there's our very, very first program. So let's give it a run. I'm going to call a program, I'm going to run a program called Clang. And I'm going to run it on Hello World C and press enter. Nothing happened. Why might that be? Why did nothing happen? What did I just do? Pass it back. Xinjiang, right?
Well, you didn't designate a place to put the output.
So let's see what's in my directory now with the ls command. Oh, there is a new file, a.out. So it did something, but it didn't produce hello world on the screen. Do you want to pass the microphone back? I'll run it over to Yash.
You compiled the file?
That's exactly right. What we did was not actually running the program itself. We were doing this translation process that I mentioned before. So all we've done is we've converted the plain English words in our hello world file into something that computer understands, but we haven't actually told the computer to do it yet. So, where's my cursor? Okay, there we go. Now I can actually run it if I want. And to tell the computer to run something in the current directory, I use this syntax on Unix-based systems, which is a dot followed by a /. And then I run the program. Hello world. Now, if I was being very fancy, I could also see what the actual instructions are inside hello world that the compiler had generated. And you're not expected to be able to do this. This is for your enlightenment. So if I run this, and what's the flag? Do you remember the flag for dash disassemble? I'm a computer scientist, not a typist. There we go. So now we can see that the compiler has turned my once beautiful simple text file, albeit with a few strange things in it, into a whole lot of numbers. And these numbers correspond to different instructions. These were the assembly instructions that we talked of before. And this is what the computer's actually running when I tell it to run hello world. It's not running the close to English text. It's running these instructions. So we've made some progress. Great. And as we go through, you'll slowly start to learn the different elements of the hello world syntax that actually make it function. For the time being, let's return to our hello world program and just look at a couple of these elements. So over here, we have something called printf, which is just like Python's print, except this one has an f in it for some reason. And instead of it being, well, I guess Python 3 uses parentheses as well. So just like in Python, we put it in parentheses, and we use a /n to indicate a new line. And then we tell the program that we're done with return. And return gives the control back from the program back to the thing that ran the program. Or in the case of a function, which we'll talk about a little later in the class, it gives control of the program back to the function that ran this function. So this function was main, and the main function is special in that it has no function that called it. It was the operating system that called it. This is the place the program starts. And so when we return from it, instead of going back to a different part of the program, we just go back to the operating system. And you can think of programs like that. It's a perfectly legitimate way to think of the operating system as one function, and then when you run a program inside the operating system, that's another function, and that function, when it's done, returns to the operating system. And we want to do no, and go back to our slides. Oh, I'm already on them. So with beautiful syntax highlighting, that's what it would have looked like.
Why are you using Nano instead of VS Code? Everyone's very confused.
Why am I using Nano instead of VS Code? Because it makes it easier to show you on the screen without having to swap windows all the time. The other thing is that it's also part of I think, a reasonable programming history to know how to edit and run commands on the terminal without resorting to additional tooling, because at some point in your career, it is quite possible that you'll get stuck and your fancy program like VS Code or your fancy text editor will stop working, like mine did when I tried to run Emacs the first time, which is a fancy terminal one. When that breaks, going back to very, very simple built-in text editing programs on the terminal can be a real lifesaver. So the two big terminal ones are Emacs and Vim, and if I told any self-respecting programmer that I used Nano in front of the whole class, they'd probably yell at me a little, but it worked. When I typed my commands into the terminal, I was actually inside a program itself. it wasn't just me raw shoving something inside the computer's memory, turning the computer on and the program executing it. There was some program inside the operating system that I was using to give the computer the commands. I called it the terminal, but the terminal is the name for the window that gives you access to the other program. The other program that was running is actually called a shell. A shell is the name that we use to refer to a program that lets us communicate directly with the operating system and run and launch and modify other programs. For the shell, you're going to have to become accustomed to a number of basic programs, either that are built into the shell or that are separate programs that come with built into the operating system. These are a few of them. This will be available in the slides after, so I'm not going to run through them one by one. But performing such basic tasks as moving things around on the computer, copying things, showing where you are, showing the contents of a file, these will all be things that you'll become familiar with as the semester moves along. On the more complicated side of commands, these are two really, really important ones for this course. These are your compilers. Again, how you'll translate your C code into running programs. We have a selection of two for you, GCC, which is more common or has been more common on Linux, and also when you install Linux on Windows, that's quite possibly the one you'll see, and Clang, the one that comes with Mac OS. Now, we really don't mind which you use. My view is that Clang has a bit of a nicer error output, so if you make a mistake, I think Clang gives you a little bit better error messages. But GCC has a much larger community behind it, which means GCC has a lot of different features, most of which you won't use. But it's worth knowing that there are some very subtle differences between the two, which most of the time won't matter to you. For reference, Clang is mostly maintained by Apple or is Apple supported, whereas GCC is supported by and maintained by the same group of people, broadly speaking, that run Linux, and the Free Software Foundation, which is an activist organization dedicated to preserving software freedom. So as part of preparation for this course, I sent an email to a friend, and he had a little bit of a message for all of you. So, Brian Kernighan and Dennis Ritchie, okay. Oh, that's the book they wrote? Oh, and this is Brian Kernighan.
To all the students in Foundations of Algorithms at the University of Melbourne. I'm Brian Kernighan. I teach computer science at Princeton University in the United States. I wrote the first book on C along with Dennis Ritchie, and I helped build some of the early Unix tools like the awk programming language. I hope you're all enjoying learning everything there is to know about algorithms. Good luck with the rest of your semester.
So hopefully that should give you a little more inspiration for the rest of semester, knowing that there's someone on the other side of the world who's thinking of each and every one of you and hoping that you enjoy your journey through the C programming language. Why can't we just run Hello World right off the bat? Assuming that I called my program Hello World, why did I need the /? And there is a hint. The hint is all around. Okay. You've answered a few too many times. Someone else. You had an answer?
Maybe.
What was your name again?
Leto.
Leto?
Because you need to be on the current directory that has it.
So that's close. Oh, I guess I'm wearing the microphone. That's close. What about another answer? Why couldn't we just run the program right like that? Yeah. Name?
Eugen.
Eugen.
So what I think is, it's /, and usually / means connecting to some directory, yeah? And dot means just the previous are just out of the way. So like everything what was behind is just as a dot, and then / and then the hello world means the path of...
exactly,
yeah,
path.
towards the
There we've got in our
world.
slide, we've got the path. And so that was a very, very good answer. The more complete explanation is that the computer at any given time has many, many programs residing all over it. And somehow it needs to know when you type something in, which of those places you want to look. And so the computer keeps a variable called the path variable that stores a list of all the places that it should look immediately when you type in commands. The current directory is not always part of that. So in order to get the computer to run a program in the current directory, rather than the one that is in the predefined set of locations in the path variable, you have to add the dot slash. The dot slash referring to the current directory, inside the current directory, and then hello world, or whatever the name of your program is. Okay. Ooh. Okay, unfortunately no magic for me today. I thought that would work, but no luck. I'm not a wizard, Harry. Basic input and output. So now that we know how to actually write a program, we need to know how to write a useful program, which means we need some ability to get things in the computer and subsequently to get things out of them. Ooh. This is an example of a program that we're about to write by hand again that shows how to do this. Okay, back to our code directory, and let's try write some code again. And so we'll call this basic io.c. So do you remember comments from Python? This is a comment in C. But we also have another way of making a comment. And as before, my spelling is only decreasing in quality the further down the class we go. That does say multi-line. Okay, so right now we have a program that does nothing. Great, we've made good progress in the class. But this is a helpful reminder to all of you that well-structured code and code that will pass our style test for the semester should include comments saying what the program will do. So now that we've had that little bit of nonsense, we can write something more descriptive. This program will read in 2 numbers and output 2 numbers. And hey, I can even type blind. Okay, back to our weird include message. Include. This is TDIO. So one of the beautiful things that Python has, but that C does not have, is batteries included. In Python, all the basic functions that you want to use are already there for you to just tell the Python interpreter to run immediately. In C, it's a little different. The language standard doesn't really specify very many things that the language has built in. Instead, it specifies just a bunch of building blocks to put together. But it would be a real chore if for every program we wanted to write, we had to go from the smallest building blocks up to some basic operating system functions. And so, helpfully, when you install your C compiler in your operating system, it comes with built-in headers. These are standard io.h and standard lib.h, and there are a whole bunch more of them. And the function of these is to tell the C compiler that actually, yes, instead of just using the raw building blocks, I'm going to use some pre-written code that's stored elsewhere on the computer. In this case, we're including the standard library, and we're including standard input and output functions. And now we're back ready to write our main function, which is where the program starts when the operating system launches it. Only this time, I'm going to use a different variant of the introductory arguments. Both of those are valid, and we'll see why in a later lecture. So, any guesses for what this line does? Not from Yash.
It's seek.
Seek.
It basically initializes a variable.
And why do we need an initialize a variable?
To tell like the compiler that to allocate a certain amount of memory for the compiler to hold a value later on.
Exactly. Great answer. So Zeke got it right. Unlike in Python, in C we need to explicitly tell the computer that we want to have room for where we're going to store our variables. In this case, this is how we would store a make room for an integer variable. Now, another big difference that we're going to see from Python and from many other programming languages is that C is typed. That means not only do you need to tell the computer that you want some space for something, you need to tell it what you want space for. Any guesses why? Why do we need to tell the computer what we want space for? Yes?
So the computer can work out how much memory it needs?
Exactly. If we want to store, say, a big set of numbers, we're going to need to tell the computer that we want space for a certain set. If we're going to want to store something with a lot of decimal points, we're going to need to tell the computer that we need space for the number and all the decimal points. And if we only want to store a single letter, well, there's no reason for the computer to waste space for thousands of words. We need a way to tell the computer exactly what we want. And C gives us this command and this control over exactly what the underlying computer is doing and how much memory it's using. So I've created an integer, and now I'm going to create a double. And I think this course might still have it, I don't remember, but there are two different kinds of, or at least two different kinds of numbers with decimal points in C that you can allocate. Float, which stands for floating point, and double, which means double precision. Now, my personal recommendation, and I don't remember what was written in the textbook, I'll have to check it later, but that is, in life, one should never use floats. They are now outdated because they have all these issues associated with them, some of which we'll actually see. Floats have a very limited precision. This means after a few decimal points, the computer starts sacrificing some of the accuracy of the calculations you do in return for improvements on space. So with a double, it takes a lot more memory to store, but with a float, you can be really efficient. Unfortunately, it's a big source of potential errors in your code, and so in real life, I would probably encourage you to think very carefully before you use a float. Okay, so we've gotten that far. Now we've allocated some memory, but we're still not doing anything, so that's not particularly interesting. Finally, a function that will actually do something. But this function isn't totally clear. It's got a whole lot of weird symbols, and it's not obvious what it's doing. Well, this is our brief interlude to the man pages. It's quite possible I have. Yes, I did miss one. And we'll go back and fix that in a minute. But thank you for spotting that. And this will happen consistently to you as well. When you are writing your C code, you'll make mistakes. It's part of the game. So this is our interlude to the man pages. Man is short for, any guesses? Just shout it out. Manual. And so I use this function called scanf. And we didn't know what it was. It's not as obvious a name as print, now that we know what print is. So what we can do is we can go to our terminal and type in man scanf. And there is our manual. It explains what the function does. So we might have to scroll a little bit because the man page is pretty large. The scanf family of functions scans input according to a format as described below. The format may contain conversion specifiers, so maybe to allow us to convert what's written by the user into a different format. And it reads input from the standard input stream, and there are other ways of reading from other input streams. We're not going to bother with the details right now, other than to note that the man pages are a really useful resource. We're also going to post on the LMS a simplified version of the man pages, a link to a course at a different university that's prepared these to enable you to read plain English summaries and toggle between the more complex version like the full man pages and the simplified man pages as you begin to be accustomed with the C programming language. So let's go back to our program, and first things first, we missed a quotation. And now that we know at least what this does, maybe we can have a guess at what some of the different components of the function call of using the function are. At the start of the function, we have some kind of string, something in quotation marks, and then we have the names of our two variables. Well, remember when we read the man pages, it said that one of the key aspects of this function was the ability to perform conversions. And so that's what's going to be done in our format string here. It makes sense if we already know where we're storing things. We've got to put in what kinds of things we're storing in and how to convert them. In this case, the %d will be our format specifier, or our conversion specifier, that tells the computer that the next thing we read in is going to be an integer. And then LF is going to be our format specifier for reading in a long float, which is another word for a double. That's what LF stands for. You don't need to remember what it stands for, though. You just need to remember that LF is the format specifier for a float. Then we have the two variables. And we're definitely going to come back to this syntax, but for now, just think about it as this tells the function to store the values inside those variables. And there's going to be something pretty nifty about the way that that's done that we'll come to, I think, in week 3. OK, so we've read a few things in. Now I'm going to do something a little funky. OK, you'll notice that this line is not indented properly. Doesn't matter. The answer in C is no. C is white space agnostic. So if I put my line there, this program is still going to run. Doesn't mean it's a good idea, but I just wanted you to see that that for the sake of a correct program, it doesn't actually matter. So now we've written our basic program, and in the last dying minute of the class, let's see if it runs. We've told print to print n and x, and this time with the format specifier for d and for a float for print. You can just run it right out. So let's run clang. And this time we're going to tell it to put it in a program called basic IO. Tells us that it has successfully stored 5 and 7.8 inside those variables. And with that, that is your welcome to C, your very first lecture. You're now equipped to go and write whatever, well, almost whatever program you like. I will catch you all next week. Have a wonderful weekend, and it's time to start writing some programs. Thank you very much.